On August 30th, 2026, NASA is launching a space telescope so powerful that it will photograph more of the universe in a single day than Hubble has captured in its entire 36-year career. It has a field of view 100 times larger than Hubble's. Over its 5-year mission, it will measure light from 1 billion galaxies, discover up to 100,000 new planets outside our solar system, and collect 20,000 terabytes of data, more than any telescope in history. It is called the Nancy Grace Roman Space Telescope. This is the story of the most powerful space telescope humanity has ever built, what it is about to show us, and why what it finds could permanently change our understanding of the universe. To understand why Roman matters, you first need to understand what Hubble cannot do. And that requires stepping back for a moment to appreciate just how extraordinary Hubble actually is, before explaining why it is not enough. The Hubble Space Telescope launched in 1990 and has been one of the most productive scientific instruments in human history. It has taken over 1.5 million observations. It has helped determine the age of the universe. It has shown us galaxies forming shortly after the Big Bang, black holes at the centers of almost every large galaxy, and planetary systems forming around young stars. When most people picture what space actually looks like, they are picturing what Hubble showed them. But Hubble has a fundamental limitation that no amount of engineering can fix. Its field of view is tiny. When Hubble photographs a patch of sky, it sees an area roughly the size of a grain of sand held at arm's length. That is extraordinary precision. But it means building a complete picture of the universe through Hubble is like trying to map an entire continent by looking through a drinking straw. You can see extraordinary detail, but you can only see one tiny spot at a time. Covering enough sky to answer questions about how the universe is structured on the largest scales, questions about dark matter, dark energy, the distribution of galaxies across billions of light years, would take Hubble longer than the age of the universe itself. Roman solves this problem. Its wide field instrument sees 100 times more sky than Hubble in a single exposure, at the same extraordinary resolution. Same quality, 100 times the width. Before we talk about what Roman will find, there is a story worth telling. Because like Parker's solar probe, this telescope carries the name of a real person, and her story is one of the most important untold chapters in the history of space exploration. Nancy Grace Roman was born in 1925 and fell in love with astronomy as a child. In the 1950s, she joined NASA before it was even called NASA, becoming the agency's first chief of astronomy in 1959, one of the first women to hold an executive position at the agency. At a time when women in science were told explicitly that their careers had a ceiling, she simply kept going anyway.
I certainly did not receive any encouragement. I was told from the beginning that women could not be scientists.
Roman spent decades fighting for the idea that a space-based telescope, above the blur of Earth's atmosphere, would transform astronomy in ways that no ground-based observatory ever could. She championed what eventually became the Hubble Space Telescope through years of bureaucratic resistance and budget battles, long before a single mirror had been polished. She never got to see Hubble reach its full potential. She passed away in 2018 at the age of 93. But the observatory she spent her career making possible has now captured over 1 million images and redefined what humanity knows about the cosmos. The telescope that bears her name will see 100 times more of that cosmos with every image it takes. It is, in a very real sense, the telescope she spent her life building. She just never knew it would be this big. Here's a fact about the universe that most people have never fully absorbed. Everything we have ever seen, photographed, or detected, every star, every galaxy, every nebula, every planet, every black hole, makes up approximately 5% of everything that exists. The other 95% is completely invisible to us. We cannot see it, we cannot touch it. We can only infer its existence from the way it affects the things we can see. That invisible 95% is divided into two components. About 27% is dark matter, a substance that does not emit or reflect light, but which exerts gravitational pull. We know it exists because galaxies rotate in ways that only make sense if there is far more mass present than we can see. Without dark matter, galaxies would fly apart. It is the invisible scaffolding that holds the large-scale structure of the universe together, and we have no idea what it actually is. The other 68% is even stranger. It is called dark energy, and it is the force driving the universe to expand at an accelerating rate. The existence of dark energy was only discovered in 1998 when two teams of astronomers studying distant supernovae, the violent explosions of dying stars, found that the universe was not just expanding, but accelerating. Something was pushing galaxies apart, faster and faster, and nobody knew what it was. That discovery won the Nobel Prize in Physics in 2011, and we still have no explanation for what dark energy actually is or where it comes from. Roman's primary mission is to investigate both. By mapping the distribution of hundreds of millions of galaxies across billions of light-years and measuring precisely how the universe has expanded over time, Roman will give scientists the most detailed picture ever assembled of how dark matter and dark energy have shaped the cosmos. If any telescope can crack the mystery of the missing 95% of the universe, it is this one. Dark matter and dark energy are Roman's headline science, but they are not the only thing it is going to find, not even close. During its survey of the central region of our own Milky Way galaxy, Roman will use a technique called gravitational microlensing to detect planets that no other telescope could find. Here is how it works. When a planet passes in front of a background star, its gravity acts like a lens and briefly bends and brightens the star's light in a characteristic way. By monitoring hundreds of millions of stars simultaneously, something only Roman's wide field of view makes possible, scientists expect it to detect more than 1,000 new exoplanets through this method alone. Combined with its other detection capabilities, the total count could reach 100,000 new worlds over the mission's lifetime. To put that in context, as of today, humanity has confirmed the existence of roughly 5,700 exoplanets in total, the result of 3 decades of work by multiple space missions and thousands of ground-based telescopes. Roman may surpass that number many times over in 5 years. And crucially, because of how gravitational microlensing works, many of the planets Roman finds will be ones that other methods simply cannot detect. Smaller planets, planets far from their stars, and potentially even free-floating planets with no star at all, drifting alone through the darkness between solar systems. Some of those 100,000 worlds will inevitably be candidates for hosting life. Roman cannot tell us whether they do, but it will give the next generation of telescopes a target list that will take decades to work through. On August 30th, 2026, Roman lifts off on a SpaceX Falcon Heavy from Kennedy Space Center in Florida. It will travel to a point in space called the Sun-Earth L2 Lagrange point, roughly 1.5 million kilometers directly behind Earth relative to the Sun, the same gravitational sweet spot where the James Webb Space Telescope currently operates. At L2, a spacecraft stays in a stable position relative to Earth while having an unobstructed view of the entire sky, shielded from the Sun's heat and light by Earth itself. Within weeks of arriving, Roman will begin commissioning, aligning its mirrors, calibrating its instruments, testing every system on board. And then it will start doing what it was built to do: sweep the sky in wide infrared swaths, night after night, building the largest and most detailed survey of the cosmos ever attempted. By the end of its 5-year primary mission, Roman is expected to amass a data archive of 20,000 terabytes. To give you a sense of what that means, 20,000 terabytes is roughly equivalent to the text of 4 trillion books. No single human being could read that much data in multiple lifetimes. Analyzing it will require artificial intelligence, machine learning systems trained to recognize patterns in data at a scale no human eye could process. The discoveries buried inside Roman's data archive will be coming out for decades after the telescope itself stops transmitting. And here is the detail that makes astronomers most excited. Roman and Webb are going to work together. Webb sees tiny patches of sky in extraordinary depth and detail. Roman sees enormous swaths of sky at Hubble resolution. Together, they function like a zoom lens and a wide-angle lens on the same camera. Webb zooming in on the most interesting objects Roman identifies, Roman providing the context and scale that Webb cannot capture alone. The two telescopes operating simultaneously represent the most powerful combination of space-based observatories in history. In 30 years, Hubble changed everything we thought we knew about the universe. It showed us the age of the cosmos, the violence of its early history, the black holes at its centers, and the planetary systems forming around its stars. It did all of that through a field of view the size of a grain of sand. Roman has a field of view 100 times wider, and it launches in 84 days. One of the scientists leading the Roman project put it this way: if Roman wins a Nobel Prize, it will probably be for something we have not even thought about or questioned yet. That is not a marketing line. That is what happens when you build an instrument powerful enough to see things no one has ever seen before. You stop finding what you were looking for and start finding things you did not know existed. The universe has been out there for 13.8 billion years, holding its secrets. Roman is about to go look at 1 billion galaxies worth of them at once. If this video gave you something to think about, the like button genuinely helps the algorithm show it to more people who would appreciate it. Subscribe if you want to be here for the next one, because we are going to look at what happens when an asteroid the size of the Eiffel Tower flies closer to Earth than our own satellites. It happens in 2029, and NASA already knows exactly what to expect.